Alright, y'all, this video is going to talk about U substitution when solving antiderivatives. Okay, first of all, we need to know when using U substitution is helpful. Okay, so I pulled up a few examples of some that are definitely U substitutions. We're going to talk about how to recognize them and what our strategies are for picking the appropriate U value. Okay, so this first one here, okay, take a look at it. We've got z times the square root with an expression underneath. Okay, next one here, we've got 3x squared with an e value. Again, we've got an exponent there with x in it. Okay, on this next one, okay, we've got an expression on top with x, expression on the bottom with x. The things that these share is all of them have a variable in two places. Okay, so what you're going to do is look for how many variables show up, or how many times a variable shows up in the problem, okay? And if that is separated by times or division, that's a U substitution. Okay, so right here we've got our variable in two different places. This says z times the square root of this 4z squared minus 5. We're going to substitute. Okay, on this next one, it says 3x squared times e to the 2x cubed. That's a substitution problem. Okay, same thing here. We've got x plus 3 divided by. If it's multiplication or division, we'll substitute. Okay, so now let's talk about what to substitute where. Okay, so first couple examples here is dealing with a root or raised to a power because they deal with the same kind of idea. We've talked about this before. The square root of x is the same thing as x to the 1/2 power. So if you've got some expression underneath a square root or some expression to a power, that's going to be the u that we choose. Okay, so let's look at this one. We've got underneath this root, this whole thing, that's going to be our u value. Okay, so 4z squared minus 5, and then we find our derivative of that with respect to z. So that's 8z, constant goes away. And then we're going to try to make this original look the same value, just using u's instead of z as our variable. Okay, it has to be exactly equivalent. So we're going to start with this power to begin with. Okay, this x to the 1/2 is important because it's replacing the root. So here, this whole part is going to be replaced by u to the 1/2 power. Okay, so I'm going to start with that, just over here to the side because that's where it's shown up here. So the whole expression, okay, becomes, and I'm going to start with just the original, show you directly how they relate. So this was our z. This whole part just becomes a u to the 1/2. Okay, the second part is going to be what's on the front end and this back end together in one go. Okay, so our du is going to replace both of these in some way. Sometimes it's directly, and sometimes we have to manipulate the du a little bit to make this work. Okay, so what I'm going to do is go ahead and call this du and see what that would look like. Okay, du would be 8z dz. So instead of z dz, it's got this 8 in front. Okay, it's really important that these are exactly equivalent. So what we can do to cancel out that 8 is use a 1/8 out in front. Okay, you can do it inside or outside. I like to just pull those constants out. Okay, now this causes a lot of struggle for some folks to see this, so I'm going to show you a way where you can figure out what needs to happen here every single time, if you're one of those people who do find it a little bit challenging. Okay, you can come over here, and the whole idea is that these two pieces are going to work together to go with this du. So you're going to go to your du and solve for your dz. Okay, so how that looks is we're going to move over this 8z, dividing it. So that means for dz we can substitute this whole thing. So if I put this right here, and I'm only concentrating on these pieces, okay, it would look like z times this du over 8z. Those z's cancel out, and there's that 1/8 du front and back with the substitution. Okay, so if you struggle, try that. But now we're able to use our power rule to finish this out without having to worry about all the crazy stuff that's being taken place by u. So here our 1/8 just stays, and our u goes 1/2 plus 1 to our power, and we're dividing by that same thing, the 1/2 plus 1. Okay, so take as many steps as you need to here. Keep your 1/8, and then this part is u to the 3/2 over 3/2. Okay, and I don't like dividing by that fraction. I'll usually skip this step entirely, but dividing by 3/2 is the same as multiplying by the reciprocal, 2/3. And then we got something that looks a lot nicer. Okay, all of these we have this constant attached. Okay, we want to make sure that's included. And then we're going to simplify and resubstitute with our 4z squared minus 5. Okay, so here we can simplify a little, call it 1 over 12. And then u to the 3/2 power would look like 1/12 4z squared minus 5 to the 3/2 plus our constant. And that's it. Now what I want you to do for first couple ones here, or until you feel really good about working backwards, is just take an extra step to check yourself. Okay, that's something that's real nice about these. You've got a check built in. You find the derivative of this thing if it's equivalent to the original you did it. Okay, so if we're working back through our derivative, that would look like 3/2 times 1/12, and our 4z squared minus 5, decreasing that by 1 would look like 1/2. And then it's chain rule because we've got some things inside here other than just z. So derivative of the inside would be 8z, and then we simplify. Okay, so right here, I want to show you how this is related to this process we just did. If you look at this, this is 3 over 24. Well, that's 1/8. Okay, there's our 1/8, and there's our 8z that we were talking about. Okay, so those cancel each other out, just like we wanted to give us that z, which we usually put first. Okay, so this is exactly equivalent to the original, because remember 1/2 is just the square root of it, so we're good to go. Okay, you can always check yourself for these. Okay, let's look at this next example. It's actually with e and a power here. Okay, when we're dealing with our exponential functions base e, we want to use the power as u. So that is going to be directly our u value, just the 2x cubed. And that would make du 6x squared dx. Okay, so we're making our substitution. This 3x squared should relate to this. If I'm trying to get to 6x squared, or get to 3x squared from 6x squared, excuse me, we need to half it. So 1/2 can go outside. And then this e is going to be to the u power du. Now I'm going to show you this 1/2 du again, just so we get familiar with this. This should be equivalent to this part. So let's go manipulate this for a second here. Okay, so if you struggle with this part, here's what I want you to do. We're going to just get dx by itself. So that would look like du divided by that 6x squared. And we're going to take and sub it in right there. 3x squared times dx would be times du over 6x squared. X squareds cancel. 3 over 6 is 1/2. It's coming right there. Okay, the 1/2 du is what we're trading. Okay? Alright, so now that we've got this, we're going to go ahead and do our antiderivative rule here. Remember, the derivative of e to the x is itself. Same thing with antiderivative. Okay, we're just leaving it alone, adding the constant. Now we can sub back in. Our u value was 2x cubed, and that is it for this one. Alright, next up we've got a quotient here. So when we've got this, we want to use the denominator as our u value. In this case, we've got the denominator to a power, so we're going to let this just expression that's raised to the power be the u value. Okay, so x squared plus 6x. Okay, and then du would look like 2x plus 6. I'm going to hug that with parentheses, dx. Okay, so this is the expression we're trying to make look like our second part, our missing part. So if you notice that this thing is double that thing, both pieces, so we'd need a constant of 1/2. Okay, but I'm showing you the same way I have been showing you. Okay, if we divide that over, this is our dx, and we can substitute it. So x plus 3 times du over 2x plus 6. This one's a little bit tougher to see, but there's a GCF here that you can factor out. And there's our 1/2 du. Okay, so now with our substitution, we've got our 1/2 and our du, and this thing squared is in the denominator. Okay, so take as many steps as you need to. Okay, so if you need to write this first before changing it to your u to the negative second power, please do. And now we can use our rule on it. Okay, so from here we're adding to our power and dividing by that same thing. Simplify as you go if you'd like. So here, a negative 2 plus 1 is a negative 1. And I'm dividing by negative 1 as well. Okay, dividing by negative 1 just puts a negative out here. That's okay. And then we can substitute and rearrange if we'd like. So negative 1/2, this is x squared plus 6x to the negative 1 power. Okay, rewriting, I mean by this, we a lot of times like it in the original form. So that would look like a negative 1 on top, and this 2 times our x squared plus 6x to the first power on the bottom. Okay? And then remember, you can always check yourself by taking the derivative of that thing, checking it back with the original. Alright, next up is a little bit different. Okay, we still have the variable in two places, so it's still use substitution. I'm going to show you the problem as we try to do our normal substitution. Okay, so just like we have been doing, when we see something to a power, that expression is our u. Okay, so that's p plus 1. The problem is when you do the derivative of that with respect to p, you just get 1. And why that's a problem is because this part is supposed to pick up the front part. Okay? Well, that's not picking up our variable p, so we're a little bit stuck there. Okay, there's no way to solve for this and get a constant. It's not going to work that way. So instead of manipulating the second part, we actually have to manipulate the first part. Our job is to get something that looks like p happening. Okay, so to do that, you just get p by itself here, subtract the 1 over. So p is going to be u minus 1. So we actually have to make a substitution with 3 parts here, okay, all of them, not just 2 of them. So here, the first one, p is substituted with u minus 1. And anytime we've got 2 terms, we're putting parentheses around it. It tells us order of operations. The second part, p plus 1 is u. Okay, so we can just call that u to the 5th. And our dp, we still have to get by itself. Dividing by 1 is just du. So there's our expression, which is completely different than what we've been doing before, but realizing we still just have to make sure that our substitution is exactly equivalent to the original based on how we set it up. Okay, now here's another problem. We've got a variable in 2 places. Okay, that's what we've been trying to avoid with this u substitution, because this looks like a product rule, and we can't undo a product rule. We can undo a chain rule, but with product rule, it requires a different process that you don't know yet. Okay, so with this substitution, not only is the setup a little bit different, you have to take another step from here. Okay, I'm not going to give you ones that you aren't able to do, right now you can't do this with a product rule, but because this u to the fifth is by itself, and this is just an expression to the first power, we're allowed to distribute through and simplify. Okay, so that is u to the sixth minus u to the fifth. And now it's something a lot nicer. We still got a variable in two places, but it's separated by a plus or minus, not by a times like it was here. Okay, so let me make really clear the difference between why we still use substituted versus doing this to begin with. Okay, so up above we had times, but the problem is this p plus 1 was to the fifth power, not the p. To do that, we would literally have to write p plus 1 5 times, and we'd have to FOIL that all out. Okay, there's a shortcut, but you probably don't know it for a fifth power. Okay, so we did the substitution, and that allowed us to have a expression that we actually could simplify. And now that we can simplify it, we can find the derivative, or the antiderivative of both parts. So using our power rule, we're increasing by 1, dividing by that same thing. Increasing by 1, dividing by that same thing. And from here, we can step back in. So p plus 1 to the 7th power over 7. If you like that 1/7 in front, that's equivalent. It's up to you. And then the p plus 1 to the 6th power over 6 plus our constant, and we're done. Okay? For these ones, sometimes they're going to have you do a little bit of factoring. So how that would look if they want you to simplify this a little bit more, I'm going to go ahead and rewrite that with the 1/7. This is p plus 1 to the 7th minus 1/6, p plus 1 to the 6th. Okay, with this part right here, this p plus 1 to the 6th power is in common. So how that would look inside, the 1/7 stays. This one has an extra p plus 1. And this part, we factored all of that out, so it's just minus 1/6. So this would be an equivalent expression. I like to only factor out when it makes it look nicer, things cancel out. In this case, that didn't happen, okay, so I would be good with either. Last thing is talking about word problems, how antiderivatives can be used to solve problems like this one. Okay, it says a company has found the marginal cost, and this word right here is super important, in thousands of dollars to produce X central air conditioning units. They give us this equation, says X is the number of units produced. Okay, so this marginal cost is talking about the rate of the cost, okay, or how the cost is changing. Okay, that's directed to our slope. It's telling you the derivative is happening. Okay, another thing they could do instead of giving you that vocab is they may just give you the notation. Okay, these two things mean you have the derivative. Part A says find the cost function. This says find the antiderivative because we have the derivative and we want the regular, the original function. So we're going to find that cost function by using the antiderivative, and a lot of times with our application problems that means we have to go find C, that constant, so we can plug it in. So it says they gave us that the company incurs a fixed cost of $10,000 even if no units are built. So this is an ordered pair, but based on the information they gave us, we have to be careful. Okay, our no units is our X value, so that's definitely 0. But this 10,000 relates to the cost that they gave us, and it says in thousands of dollars. So if it's 10,000, that would be 10 in thousands. Okay, so be careful with those. They are tricky. So let's go to work. We want to find the antiderivative of this thing, this 60x divided by 5x squared plus e. And we're doing that with respect to our variable x. Okay, so we are going to recognize that there is an x in two places separated by division, so it is u substitution. And when it's division and there's no power, you're going to the denominator. That's going to be your u. So that's 5x squared plus e. Derivative of that is 10x. What's really important here, y'all, is e is just a number. Okay, it is a constant unless there's an x attached to it. So that e goes away, and there's our dx. Okay, we need this to look like 60, so you'd have to multiply by 6. That's our constant. Okay, but just like I have been doing, you divide by that, and you can substitute in to find it as well. So 60x dx would look like 60x times this thing right here, du over 10x. And there's 60 divided by 10 is 6 du. Tells you the same thing. Okay, so 6 goes out, du goes to the side, and let's deal with this thing. Okay, so here's our u value that we substituted. It's on the bottom, so that's 1 over u. Okay, this is a special case, and I'll show you how to recognize it's a special case. Okay, if you try to use your power rule on this, you would have some problems. Okay, so if you use your power rule, it's because you rewrote this as u to the negative first power. And that would look like u to the negative 1 plus 1 divided by negative 1 plus 1. Here's the huge problem. This is dividing by 0, which is not allowed, folks. Okay, so if you ever get to that step, that should trigger your memory that this is not power rule. Instead, we're going to flash back here and remember that antiderivatives is just going backwards from a derivative. Okay, so the natural log of x was equal to 1 over x. Okay, with that, we're going backwards. We've got our 1 over u here. It goes to the natural log of u. So this is 6 natural log u plus our constant. Subbing back in, we've got our function being 6 natural log of our 5x squared plus e, and there is some constant that we have to figure out. And that's where this ordered pair is going to come into play. We've got our x value and our y value that we can sub in. So this is our fancy y value, 10. 6 natural log, 0 is going right here. So 5 times 0 squared is just 0, plus our e, plus our constant. Okay, 5 times 0 is just 0. So this is 10 is 6 natural log e plus c. Natural log of e is just 1. Okay, if you don't know that, your calculator does. 6 times 1 is 6. And that tells us our constant is 4. And it's really 4,000. Remember, okay, we're talking about this cost in thousands. So, final cost function, 6 natural log of our big mess here, 5x squared plus e plus our constant. Okay, that's part A. Then if we go look at part B here, it says the company will seek a new source of investment income if the cost is more than 20,000 to produce 5 units. So they don't want to exceed 20,000 if we're plugging in 5. Okay, so let's go plug in 5 and see if it goes over 20,000 or not. Okay, so 5 is going right here. All of this can be done in your calculator if you want. Okay, I've simplified it here already. 6 natural log, your 125 plus our e, and this is 33. Remember, it's in thousands, so 33,000. So because 33,000 is greater than our 20,000, then I would say yes, they need to seek that new source of investment income. Okay? Hopefully this helped clear up U substitution, the process, when to use it. Okay, but remember, if you have any questions, please reach out.